Okay, let's continue talking about electric fields for different charge distributions. What if we have two positive charges as opposed to just one? Okay, well let's start with just some easy situations. If our test charge, remember our little imaginary proton was over here, it would be being repelled by both this charge and this charge. Probably repel to the right, right? Because like charges would repel. I agree. Probably repel in this sort of direction. Same thing over here on the left. On the left, it should, let's see, it'll be repelled by both this and this. The electric field line probably points like this because the test charge would experience a force in that direction. Again, remember, the size of the lines doesn't really mean anything. And I think we can assume if it's on the exact line directly connecting the centers here, like imagine it was right here, well, it's going to be repelled by this one to the right, it's going to be repelled by this one to the left. But which one is it closer to? It's closer to this one on the left, so that means the repulsion is probably stronger from this one. Remember, the force is what we're looking at here. The force on this proton that's closer to this one, if R is smaller, then that means that there should be a greater force pushing it to the right than to the left. And where would that stop? That would probably stop right about in the middle, right? Because in the middle, now it's experiencing exactly the same forces from both sides. So I'd have a field line going like this, right about to the middle, and I have a field line going like this. Oh, sorry, that's a little curve there. Remember my rule about things shouldn't cross? Right about to the middle. It's in other places that it's a little bit trickier. Let's start, let's say here, okay? If you put a proton here, then the electric field, then the force is going to be very, very strong from this object, not quite as strong from this one. Okay, so if you put a force here, the force probably starts by pointing kind of out in this direction. But what happens as you go out farther away from this one? You're getting farther away from this charge. The electrostatic force from this charge should decrease. Aren't you kind of getting closer to this charge? It seems like you are. You might be getting a little bit closer. It seems like the force from this charge, if it isn't increasing, at least it might, maybe it's staying the same. Maybe you're staying about the same distance away. But think about what that's going to do. You have a force from this charge that is pushing kind of up and to the right. As you get closer to this charge, you're going to have maybe a bigger force pushing away up and to the left. So since we have two different forces arising from two different charges, we're going to have something that maybe looks a little bit strange here. What's going to happen if you have a part, the field line, if you're kind of above, kind of like off at a diagonal, either of these places, is your field line is going to look kind of like this. It's going to curve upward like that, okay? And that is just because as you get farther away from one charge and maybe a little bit closer to the other, the imaginary electrostatic forces from each charge are going to change their strength. And as they change their strength, okay, as they change their strength, they're also going to be changing direction because you're moving out a little bit. So as they change their strength and direction, the direction of the electric field line, the electrostatic force, I guess you could call it the net electrostatic force that they feel from both charges, is going to change as well. The nice thing is they're kind of symmetric, so what one looks like, the other one kind of mirrors. Eventually, what's going to happen is if you get right between the two charges, but up here, the horizontal component from this charge of the force is going to cancel out with the horizontal component from this charge, but they're still going to have the vertical components that work, or that are the same. And so what you'll have is basically an electric field line that just kind of curves up like this. Okay? All right. We can kind of have the same talk for a lot of these. If you're directly above one of the charges, at first the field line is going to point straight away. But as you get farther away from that charge, as you continue to go up, you're going to have the field line kind of curve around like this, because now the field is not going to, or this force is not going to be as strong from this charge. And well, the force is decreasing from this one as well, just not quite at the same rate. You can have a field line kind of like that. And I'm going to fill in the rest of the field lines. I mean, a lot of them you can probably kind of guess at. because they look very similar to each other. And again, like I said, this is something that's a little bit hard to explain virtually. I can try and find some resources for you guys to maybe go on your computer or on a phone and understand why the electric fields are in this direction. But in any case, what you end up getting here is, unless you're along this kind of central axis where the lines are straight, you get field lines that are curved. Now, it doesn't mean the force curves things around. That just means at different points, like right here, the force is kind of in this direction, tangent to the field line. Right here, the force is in this direction, tangent to the field line. Okay? So when you have two or more charges, you usually get curved field lines. If you have two positive charges, those field lines curve away from each charge. And they kind of curve, I guess you could say, away from the middle. I guess that's probably the best way to put it. They're always curving away from the middle. All right? Now, what happens if you have two negative charges? It's kind of just the opposite. If you put a positive charge over here, it's going to be attracted to both those, right? Same thing over here. And in the middle, if you're right directly in the middle, it's going to be held because it's equally attracted to both here and here. But if you're just a little bit to the left, you're going to get attracted to this one. If you're just a little bit to the right, you're going to get attracted to this one. See how all these lines are just the reverse? That's a pretty good indication that all the lines are going to look like that. Remember, field lines end directly on the charges. So far what we have is we have field lines for single charges. These are very simple to remember. For a positive, they go straight radially outward. For a negative spherical charge, they go symmetrically, radially inward. For two positive charges, they still go away from the positive charges, but they kind of curve away from where the charges are. They curve away from the center area here. For the two negative charges, it's just the inverse. So far you basically have two things that you have to remember. One thing that I do want to point out is that, where is the field strongest? In this case, it's very strong close to the charges. And zero in the middle. In the exact middle, the field is zero because at this point, the force from this charge would cancel out the force from this charge. One would be pushing to the right, one would be pushing to the left. Net force is zero. And again, here, the field is strong close to the charges. And it's zero in the middle. Okay, we have two more charge distributions that you need to know. Basically, these six, I tell you guys, you don't have to memorize a heck of a lot in this class. These should be memorized, okay? You should memorize each of these charge distributions because it makes it very easy. One positive, one negative charge. Well, let's do the easy cases first. Right in the middle, if you put a proton right in the middle, it's going to be repelled from the positive and it's going to be attracted to the negative. So you're just going to have a field line like this. Okay, notice it starts on a positive, ends on a negative. What if you're over here? If you have a proton over here, well, it's going to be repelled by the positive and attracted by the negative charge, but which one's it closer to? It's much closer to the negative charge. So what that tells us is that attraction to the negative charge is going to be stronger than the repulsion from the positive charge. Remember that when we're talking about attraction and repulsion, we're talking about the electrostatic force. So if R is smaller, the force is bigger. Since R, the distance between our test charge and the negative charge, is smaller, that's going to be a bigger force between these two than the force between the positive and the test charge. So out on the right-hand side of this distribution, we're going to have an arrow pointing in. Same thing, well, same sort of idea over here. Here, the repulsion from the positive charge is going to be bigger than the attraction from the negative charge. So the positive charge is going to win. It's going to repel the test charge away. going to have a line that looks like this. So already that looks kind of funky because we have arrows going all sorts of different ways. Let's try this. What if you're right here? What if you're right kind of on this like upper right-hand corner? By the way, I typically, and the Regents will ask you to draw a certain number of electric field lines. My go-to is drawing for situations like this, 8 lines of charge, okay? One from like, you can think of it as like north, south, east, west, and then northeast, northwest, southeast, southwest. So let's pretend that I'm on like this kind of northeast area here. At first, this charge is going to get repelled this way, right? But we have to remember, as it moves away, as we put this test charge farther and farther away from the positive charge, the force from the negative charge is going to be getting bigger as we move farther away from it. This force gets smaller, this force gets bigger. We know that that the test charge is going to be attracted to this and repelled by this. The ultimate shape, and again, the field line does not tell you the direction that the object takes, the path that the test charge takes. It just shows you the direction of the force at any point. You kind of get this kind of bowing over of the line, and it ends right on the negative. So let me explain. Right in the middle, imagine that you have a force from the positive charge repelling up this way. You have a force from the negative charge attracting it down this way. The vertical parts of that would cancel out. You're left with just this horizontal part. So at this point, you kind of have a tangent for a force in this sort of direction, and that's tangent to the electric field line. Likewise, down here, we have sort of the same thing. Here, we might start with a field line that's going pretty much straight up, but remember, as that force of repulsion weakens from this charge, as you go up, this is going to attract the test charge towards it. So we get this bending. It's just kind of like a bigger loop, like this. Same thing on the bottom. And then out here, we're going to get an even bigger loop that we're not even going to finish drawing. We're just going to kind of leave it like this and imply that it comes back around and ends here. Okay, so some key features here. People have called this like the spider graph or something before, or the spider chart, because it kind of does look like a spider. Remember, the lines start on positive and they end on negative, except for the ones on the axis between charges. Again, the goal of this, when we're drawing these field lines, the way we're getting these shapes is you're thinking about the force that would be on the particle at a certain point. Okay? If you think about that, you should be able to kind of understand, okay, I sort of see how these shapes get made. Okay? And again, we do need to actually memorize these shapes. Okay? That is really important to do. The last one I'm going to teach is about 2 parallel plates. Parallel plates are exactly what they sound like. You have one plate of a certain type of charge, another plate, like a flat rectangle, and imagine these kind of go into the page. So imagine like I kind of have my hands like this. These are like what parallel plates look like, okay? We have like positive and negative, or in this case it would be positive, negative, okay? So this one's all positive, this one's all negative. If you put a particle anywhere inside the parallel plate, it's going to be repelled, a test charge, it's going to be repelled from the positives and attracted towards the negatives. And the neat thing about a parallel plate is that the field inside it, well, hold on, I'll get to it. Let me just draw in the arrows for right now. The field lines. The field lines look just like this. I'm only going to draw 5 here. What do you notice about the spacing between those field lines? They're pretty evenly spaced, right? What does that mean? If the field lines are evenly spaced apart, remember, the closeness of field lines implies how big the electric field is. If the field lines are all the same distance apart, that implies that the field is pretty uniform. The field is the same at all points. And the field will always point towards the negative plate. That is why parallel plates are actually a huge deal in physics and in engineering, okay? The field in here is uniform. There's a ton of different applications. For example, I don't really have time to explain it right now, but the buttons on this calculator right here, the reason they work is because they're all hooked up to a little computer network, and under these buttons is under each one of these buttons are parallel plates. Okay, parallel plates. And when I press a certain button, what that does is it compresses the plates. It actually changes the electric field within because the plates get closer together. And a computer reading that change in the electric field knows that, hey, the person just typed a 9. That's one way that we use parallel plates. Another way that we use parallel plates is we think we can actually kind of shoot electrons right inside them. Imagine I shot an electron here. E stands for electron. Which way would it go? If the electron starts getting shot in this way, what's going to happen to it? Well, it's going to get repelled by this negative plate, and it's going to get attracted by this positive plate, right? So as the electron moves, shouldn't it kind of start to eventually move up towards a positive plate? And look at that. Once it's outside, it's going to keep going in that direction. We've redirected the motion of that electron. Which way would an electron zipping through the plates move after it has left them behind? Well, it ends up moving toward the positive plate. Or in other words, away from the negative plate. This is the basis, actually, behind how old TVs and screens used to work. When we come back, we'll talk about how to actually calculate an electric field, but for right now I just need to get these, you guys can't even see that. For right now, we just need to get these fields drawn and talked about. If you have any questions on this, please let me know, because I know this is a challenging topic. Okay? I'll see you later.